about acceleration now. We've got an image of a car and a set of lights. It's stopped at the lights, and as it's moving away from the lights, it's getting faster and faster. We can tell that it's getting faster also because if we look at those increments of time, so if we've got t is equal to 0 seconds where it's stopped, and then after 1 second, it's moved this far. If it's accelerating, it's going to move further in the next second. And further again for the third arm. So we can see that this gap here is getting bigger. Okay, so the time interval's the same, but the distance travelled is larger each time, and so we are accelerating. And it also works in reverse. So we've got a picture there of an athlete who's finishing a race, and it's the same arrangement of images where the gap now is getting closer together as they slow down. So they are further apart, and then getting, as they're slowing down, getting closer together over those time increments. So this here is t equals 0 seconds, t equals 1, t equals 2, t equals 3. This is deceleration, because this gap here is decreasing. Does that make sense? Can you sort of picture what's happening here? It's often easiest to imagine in the context of a car, because that's really where we move a lot faster. And so, but this is obviously, there's no maths in that, this isn't really helpful. But average acceleration, and acceleration is given the symbol lowercase a. And if we're going to calculate the average, it could be AV, it could be AVE, or AVG. Seen all of those used to indicate that it's average acceleration, is equal to the change in velocity over the change in time. And remember that the delta symbol we're using here is talking about that the change. We can be a bit more specific in what this means in terms of the velocity. The time is just going to be what you measure for your experiment. But we're going to look a little bit more closely at velocity, and we're now going to call initial velocity u. And we're going to call final velocity v. So for our calculation of our average velocity, we're going to have v minus u on t. So the final velocity, subtract the initial velocity, divided by the amount of time that change occurred, will give us the acceleration. Our units are meters per second squared for SI units. Okay, and that's a common one for students to sort of, because you're so used to writing meters per second for velocity, it tends to creep into acceleration as well, sort of not thinking. So just be careful with that one. Let's have a look at an example. This is on page 17. A student walking across Moreville Road with a velocity of 1.5 meters per second to the east. The other thing I should mention, this is a vector quantity, and so we should also have direction. This calculation here just gives us the magnitude, it doesn't give us the direction. One dimensional motion, the sign will give us direction. But there are other cases where we might need to give a compass bearing, for example, as is the case in worked example 8. So the student walking across Moreville Road with a velocity of 1.8 metres per second east has to accelerate to a velocity of 3 metres per second east due to a fast approaching car. Probably something to do with our new roundabout. So the way to structure your answer, initial velocity is 1.5 metres per second east. Final velocity is 3 metres per second, still east. And we're told that it takes them 0.2 seconds to reach the new velocity, so t is 0.20 seconds. One of the advantages of writing out what's given, you could get marks for this, even if you make some errors in the calculation. If you've obviously correctly interpreted the question, then this can demonstrate that. But it also makes it clear which formula to use, okay? Because we want to find the acceleration. So we're going to use this formula here, v minus u on t. And then it's just a matter of substituting in 3 minus 1.5 divided by 0.2, 0. And that's going to give us, let's hope the booklet's right. That's our magnitude, but our direction was already given by our velocity vectors. And so the motion is still in the same direction. So it's still east.
Is that where it's going to be to the -2?
Oh, yeah. I just told you not to do it and I did it myself.
Are those still 1 as well then?
They are 1s because they're velocity.
Okay.
But no, that one is 2 because that one's acceleration.
Yeah.
Good pickup. Gold star. Okay, let's have a look at worked example 9. The driver of a car travelling at 16.7 metres per second north slows to a velocity of 11 metres per second north. So my initial velocity is 16.7 metres per second north. And my final velocity is 11.1 metres per second north. When they approach a school zone, this takes them 2 seconds. So t is equal to 2.00 seconds. What is their deceleration? So we're still calculating acceleration. It's still the same formula. And it's good practice to write the formula without having substituted into it first. That is your reasoning. This is your scientific reasoning as to why your answer is the way it is. And it also means that if you make a silly error, you're still going to have demonstrated your understanding. Our final velocity, subtracting our initial velocity, we're going to get a negative number. And what we end up with is negative 2.80 metres per second squared. I've got it right this time. So that negative is indicating that it's decelerating. But if we think about the direction it's facing, it's still facing north. We're still driving north, we're just driving slower in the northerly direction. So our direction's not south, it's negative that north. Does that make sense? The other way we could write it would be as a positive value south. That means the same thing. Okay, because your acceleration is in your positive acceleration. You're speeding up in the opposite direction if you like. But let's just stick with that. And then our worked example 10, a horse running in a race decelerates at 2.44 metres per second squared. So this time we have our acceleration is a negative value, 2.44 metres per second squared. at the finish line of a race, slowing to a velocity of 5.55 meters per second forward in 4 seconds. So that 5.55 is the final velocity. And it did that in 4 seconds. What was the horse's velocity as it crossed the finish line? And so this is what we want to know, is the initial velocity. So if we rearrange our formula, we can see that with A is equal to V minus U on T, then AT is equal to V minus U. And let's swap sides. Or let's divide by -1. Now we've got minus AT is equal to minus V plus U. So we'll have U is equal to V minus AT. Is that all right?
Just a question. Isn't U initial velocity?
Yeah.
So if they're crossing the finish line, would it be...
That's when they finish.
That's yeah. So a horse running in a race decelerates at the finish line of the race. So it's running the race, and then it's crossed the finish line, and then it's slowing down. So, and it's decelerating at that rate, slowing to the rate of 5.5 meters a second in 4 seconds.
Yeah.
Yep. So what we're actually finding is the initial velocity. So now I can substitute in my initial velocity will equal my final velocity, 5.55, minus 2.44 times 4.00. Okay, so if we subtract a negative, it actually becomes our adding. And we get U equals 15.3 meters per second forward. Okay, because it didn't change direction. So some of the questions will require you to be able to transpose an equation. What I did it in steps. So you can do it the same in steps. Just basically I started by multiplying both sides by t. Then I wanted a positive u, so I divided by -1. That just changed the signs. And then I moved the v over to the other side with the AT. Any questions about that?
Yeah, but A still got a -1 there.
Oh, what?
Oh, both of them.
That one's right.
Yeah, no,
That one's wrong.
Yeah.
Yeah. Look at, yeah. I need practice again.